Hey guys, how's it going? Today I am doing a lesson on action potential. And an action potential just means that we're dealing with a nerve impulse. Okay, so it's like, how do you feel? Like, how do you perceive different sensations? Like, how can you determine if something like feels like it hurts versus like a light breeze? Right? How can you distinguish between hot and cold? Well, it all starts with these receptors, which are those specialized nerve endings, right? And then the information travels through a sensory neuron. And when it travels through a sensory neuron from your last lesson, there's an interneuron that's next, right? And then it passes from that to a motor neuron, right? And that's the pathway that nerves take, but it all begins here at the receptor. Now, the reason why you perceive different sensations is because, like, if this is your spinal cord, right? If this is your spinal cord, right? And this was like a pain receptor, well, that pain receptor, right? This neuron in the spinal cord is connected to another neuron, which is connected to another neuron, which is connected to another neuron. And these neurons are all connected to each other, right? And they go all the way up to your brain. So imagine this is your brain, and you went all the way up to your brain, right? Now, when you are at your brain, right, and all these neurons are like connected to each other, right? These neurons then go to different parts of your brain. So the part of your brain that perceives sensation is called your parietal lobe. And the parietal lobe is sensation. And it's basically like the top back part of your brain. So now let's say these neurons go to the parietal lobe. Bang! Right? Here's a pain receptor. The signal traveled all the way up. It traveled all the way up to your parietal lobe. And there you feel pain. So you got to get the information to the right part of the brain so it can perceive the right kind of sensation, right? Like, for example, movement, okay? So if this is your finger, right, there could be another receptor here, and this one detects movement of finger, okay? And that sensory neuron is connected to neurons in your spinal cord. Okay, sorry, let's just draw them all. I'm just going to draw it all kind of green. There's a neuron in your spinal cord, another neuron to your spinal cord, another neuron, until you get to this part of your brain, which is called your frontal lobe. And this part of your brain is where you perceive motor movement, right? But it all starts at the receptor, and you have different receptors. You have a receptor for pain, you have a receptor for movement, you have a receptor for heat. And when it begins at these receptors, it travels through the sensory neuron. It travels then through all these like interneurons in the spinal cord, throughout these interneurons in the brain, and then these neurons go to different parts of your brain, and that's how you perceive different sensations, right? So like if you were to injure your parietal lobe, you would no longer be able to feel pain anymore. If you were to injure your frontal lobe, you wouldn't be able to move properly, right? So you shouldn't, like, if you damage any part of this, like imagine if you severed your spinal cord right here and the connection was lost. Well, that means the receptor, like let's say you're trying to feel pain, right? And this is your finger, right? If this is your finger and you're trying to feel pain, well, if you have a break here, well, you can't feel anything because the neuron connection is lost. It's been severed, and you can't feel, right? Pain, you can't move your fingers, you're basically paralyzed, and that's why paralysis happens, right? One thing about your central nervous system and the interneurons in your central nervous system, they cannot regenerate because there's no neurolemma. Okay, so the interneurons have no neurolemma, so they can't regenerate, but the sensory and the motor neuron, they have a neurolemma. And because they have a neurolemma, these guys can regenerate And so if you damage a peripheral nerve, like in your fingers, then they have the ability to come back, but they don't have the ability to come back if you damage any of the interneurons in your spinal cord or your brain. Okay, just so that you know. Now, what you guys got to know is the action potential and how a nerve impulse is transmitted. So now you got to know, like, how do you feel things? Well, you got to remember, like, the nerve is a cell, right? And so, like, if this is the nerve cell and, like, that's like, this is the receptor. So here's, like, the receptor. We'll make it really big, right? Actually, maybe not that big, so because you got to see what's going on. Okay, so what just to put it into context, right? Like, here's your receptor. So here's your receptor. It's connected to a sensory neuron, like that. So imagine this is your sensory neuron. And, like, here's your dendrite. Here's your axon, right? So what I'm doing is I'm making this receptor bigger. Okay, I'm making it bigger. So here's the receptor, okay? And the receptor is connected to the axon. Okay, let's draw a better line. Okay, so just imagine this is the receptor, and here's the axon, right? And how are you going to get the impulse from the receptor to the axon, and how do you even begin the whole process so that you can feel this sensation, right? Well, if this whole thing is the receptor, right? Like, so this whole thing is the receptor, and this is part of a sensory neuron, which is a cell. Well, then inside the cell is cytoplasm, and this part of the cell is the cell membrane that surrounds the neuron. Just like a cell membrane surrounds any kind of cell, the cell membrane surrounds the neuron. And if you look at this neuron, you're gonna see that this cell membrane has these protein channels that you guys learned about in Science 10. Okay, so there's 3 different kind of protein channels that you guys got to know. So this is the sodium channel. And this is the potassium channel. Okay, so this is the potassium channel in blue. Right, and you can see there's lots of sodium channels in red and lots of potassium channels in blue. And then we have another channel called the sodium-potassium pump. Sodium-potassium pump, which I drew in pink. Okay, so these are the channels that are on the membrane, and they're found, like, throughout the membrane, like everywhere throughout the membrane. You're going to find these sodium channels and potassium channels. Okay, and these sodium-potassium pumps, you're going to see them throughout the membrane like this. Now, the thing that you guys got to know here is, like, these channels are exclusive. Like, if it's the sodium channel, that means that the sodium channel only allows sodium in. If it's a potassium channel, that means potassium channel only lets potassium in. And if it's a sodium-potassium pump, it means it's pumping both sodium and potassium, right? So that's what the channel names mean. They correspond to what they're transporting. Now, a neuron is either in 2 states. It's either at rest or it's being stimulated. Okay, now your neurons are not always stimulated. Like, most of the time, your neurons are at rest. Like, right now you're sitting down, you're not feeling any pain, you're not tasting anything unless you're eating. Are you feeling heat, or, you know, you're probably not feeling like hot or cold, right? Because right now your neurons are at rest, they're not being stimulated. But, like, then let's say somebody pinches you, right? Well, now you are being stimulated and now you feel it, right? And the same thing goes for taste, okay? So, like, taste, like, right now if you're not eating anything, you don't taste anything, but, like, if you put a French fry on your tongue, all of a sudden you taste it, right? So now all of a sudden you're conducting a nerve impulse. So when you don't taste anything, you're at rest. And when you start tasting something, then your neuron's being stimulated, right? Okay, now if your neuron is at rest, this is the way it looks like. At rest, neurons have lots of sodiums on the outside like this. Actually, I should probably draw that in red. So you're going to have lots of sodium on the outside. So all neurons at rest, Okay, now remember, like, this part here is the extracellular fluid. The extracellular fluid just means that this is the outside fluid, outside of the cell, like, and the cytoplasm is the inside fluid inside the cell, and the extracellular fluid is the outside fluid outside the cell. So there's lots of sodium outside, okay, and then inside the cell, there's potassium. And that's what a neuron looks like at rest, okay? And the actual charge inside a neuron is negative 70 millivolts. Like, now you're like, why is it a negative if potassium is positive? Because inside the cytoplasm, I'm not drawing it, but I'll just put it in there. There's like negative chloride ions in there. There's negative amino acids that are negative. And all these negative things inside the neuron contribute to an overall like negative charge. So inside the cytoplasm, it's negative 70. And outside, it is actually more positive relative to the inside. When I say that, I could be like, okay, the extracellular fluid is negative 60 millivolts. Is negative 60 millivolts still more positive than negative 70 millivolts? Yeah, it is. Negative 60 is more positive than negative 70. But negative 80 is more negative than negative 70. Okay? All right. So you're not tasting anything, right? You're just sitting here watching this PowerPoint, and you're like, what's the point? What's the point to life? Don't worry, guys. It's going to be okay. There's a point. And hopefully we get to see each other soon. I don't know. Anyways, what was I saying? Oh, yeah. So when a neuron is at rest, so let's say you're not tasting anything, right? Then this is what your neuron looks like. There's sodium on the outside and potassium on the inside. And that's it, okay? So like that's what you need to know. Right now your neuron's at rest. But hey, look. Here's a piece of salt. Here's salt. And imagine this is your tongue. And the salt that you're eating actually has an effect. And the effect of the salt is to, look what I'm doing. I'm targeting all the sodium channels. You know what it's doing? When you have salt, that is the trigger. The trigger is open the sodium channels. Okay? So that's what's happening when you get a stimulus. So the salt is the stimulus. In response to the stimulus, what opens? Sodium channels open. Okay, nothing else, not the potassium channel. We're not worried about any other channel. We're just worried about the sodium channel because only the sodium channel is responding to the stimulus. So the sodium channel opens, and what do you think happens? Well, is sodium going to move in to the cytoplasm from the extracellular fluid? Yeah. Well, why? Because I told you, and you should remember from Science 10 that things diffuse from high concentration to a low concentration. And I have a high concentration of sodium here. So of course it's going to move. It's going to move from high to low. So all of a sudden, sodium is now entering, right? So the sodium on the outside is going away. Bye-bye, sodium. Going away, and it's entering the neural cell. Right? Now, in response to that, right, sodium channel opening, what's happening to the negative 70? Oh, well, it's not so negative anymore, right? In response to the sodium that's coming in, so the sodium's coming in, sodium channel's open, this becomes like negative 50 millivolts. Okay, now remember, is negative 50 more positive than that negative 70 we started with? Yes, it is. Okay? And neurons have what we call a threshold. And this threshold means that when the inside, right, hits this like magic number, and let's say the magic number is 50, that means all sodium channels, like let's say these, some were open and some were closed, right? When you hit what we call threshold, all sodium channels open, okay? So basically, there's a graph that you guys can do, and there's like, okay, at rest, that's negative 70. Then you hit what we call the threshold. And the threshold is negative 50. Okay? And at negative 50, at this threshold, right, all sodium channels open on the membrane. But you got to hit that threshold, okay? Let's say you had like a single piece of salt, okay? All right, so we're going to start again, okay? And like, let's say all these sodium channels are closed, right? They're not open right now. We're closing all of them. So let's say we had a single piece of salt. A single piece of salt, let's say, opens one sodium channel. So opens one sodium channel. Well, sodium will trickle in, okay? Now remember, let's pretend that we are starting again at rest, okay? So we're saying that at rest, we remember that at rest, there's sodium on the outside at rest, like lots of sodium on the outside. And at rest, there's also potassium, but that's on the inside, okay? So like here we are at rest, and we're at negative 70 millivolts at rest, okay? And then you have one single molecule of salt. Okay, one single molecule of salt is super, super tiny, right? But in response to that single molecule of salt, a sodium channel opens, okay? And then sodium trickles in. So here's sodium, right? It's trickling in. And all of a sudden you go from negative 70 to, let's say you go to negative 65 millivolts because of this trickling of sodium coming in. Well, have you hit your threshold? Your threshold is negative 50. At negative 65, you haven't hit your threshold. Remember, the threshold is your magic number. If you hit negative 50, all sodium channels open. You can see here at negative 65, still the sodium channels remain closed, okay? And let's say you eat another molecule of salt. So here's your other molecule of salt, yummy. Well, that molecule of salt, let's say it opens, okay, another sodium channel. So let's say this sodium channel that was closed, all of a sudden this sodium channel opens. Hey, guess what? More sodium starts trickling in. So what's going to happen to the inside of my neuron? What's going to happen? Well, the inside of my neuron is going to, let's say, go to negative 60 millivolts, right? Remember, it's becoming more positive, right? It started at negative 670, but we agreed that negative 60 is more positive than negative 70. So as sodium trickles in, the cytoplasm is getting more and more positive. So now we're at negative 60. But have we reached our threshold? No. So you can see all the sodium channels remain closed. But let's say, okay, you eat another molecule of salt. Oops, that was two. Let's say you eat another molecule of salt. There's another molecule of salt, and in response, that sodium channel opens. Okay, so now you get 3 sodium channels open, and guess what? When that sodium channel opens, hey, you have reached your magic number, negative 50 millivolts, right? So the stimulus is the salt. As you add more salt, more sodium channels open. And when the inside becomes positive enough to hit what we call threshold, which is negative 50, then in response to that, now all these channels, sodium channels on the membrane, okay, all these sodium channels on the membrane, I gotta redraw my membrane because sometimes they all open because you hit that magic number. Now all these sodium channels are open, they're like, and all the sodium rushes in, and now all of a sudden this becomes super, super positive, right? Because the sodium channels have all opened, and all of a sudden all the sodiums are rushing in from a high concentration to a low concentration. They're all coming in. So now all the sodium's on the inside of the cell, and their sodium is no longer on the outside of the cell, okay? And so what is happening on our diagram here is, boom, you're going to hit positive 40 millivolts. So that's how positive the inside is becoming. The inside went from negative 70, and now the inside, with all the positive sodium and positive potassium on the inside, right? It becomes so positive, it hits positive 40, and this is called depolarization. Okay, so when rest is also called polarized, that's another, you either like, sometimes it's called resting membrane potential. So you're at resting membrane potential, or you're polarized, you hit threshold, and then you become depolarized because all the sodium channels open, sodium rushes in. And then you can see we get this drop here. This drop is called repolarization. Okay, now what's happening during repolarization is this. Once you hit this magic number, positive 40, right? So positive 40 is the next magic number. At positive 40, at this peak here, sodium channels close and potassium channels open. Okay, so now you've hit positive 40. Because you hit positive 40, all these channels now shut. They slam shut. They were open, now they're closed. Okay, all these are closed now. So at positive 40, sodium channels slam shut, and guess what? It is your potassium channels that now open. Okay, so these guys were shut, but now these guys are going to open. All right. I don't know why this does this. I'm not very good at this. I'm just still learning whatever. You guys hopefully are understanding what I'm saying. Okay, so at this point here, potassium channels are open on the neural membrane. Okay, now can you guys guess what's going to happen if the potassium channels that were shut now open because you hit that positive 40 millivolt, that magic number? Where's potassium going to move? It's going to move out. It's going to move out. It's going to move from where there's a high concentration to a low concentration. So now all of a sudden the potassium ions are on the outside. Okay, they were on the inside, but now they're gone. They all went outside, right? And because they're all outside, what is happening here is you're losing potassium ions leave the cytoplasm, okay, and they're leaving and leaving, and because you're losing this positive potassium, see how potassium carries a positive charge? Because you're losing this positive potassium, what's going to happen to the polarity of the inside of the neuron? What's going to happen to the charge of the inside of the neuron? It's going to go down. In fact, it becomes more and more negative, right? The potassium is leaving. It becomes so negative, right? It hits negative 90 millivolts. That's how negative it becomes. And so you see in this graph here, a dip where it becomes so negative, it's at negative 90. And this part here, when it's that negative, is called hyperpolarized. Okay, so it's called hyperpolarized. And then, right, you go back to rest or resting membrane potential. Now, you can see here that we've had a reversal. Like at the very beginning when we were at rest here and when we were polarized, remember, sodium was on the outside and potassium was on the inside. Well, now look, potassium's on the outside, sodium's on the inside. So guess what is going to restore our resting membrane potential? Hey, it's our handy dandy sodium-potassium pump. This guy in pink. This guy in pink is also found in the neural membrane. And what this pump is going to do is it's going to pump sodium out, and it's going to pump potassium in, and it's working all the time, you know. And what it's going to do by pumping sodium in and potassium out, it's going to restore resting membrane potential. That's what's going to happen. Okay, so as this sodium-potassium pump works, you're going to see all this sodium that was on the inside and all this potassium that was on the inside. You're going to start seeing, right, that it goes back to what we began with, which was potassium on the inside and sodium on the outside. And now this membrane is back to rest. Okay, so I hope that made sense. And here's the chart that kind of you guys got to know that goes along with it. If I drew this chart out again, like some major points here, when you're at resting membrane potential, which is at negative 70 millivolts, this is what your cell looks like. It is negative on the inside, positive on the outside. And just remember that it's sodium on the outside and potassium on the inside. And then you hit that threshold, and then you depolarize. Okay, and when you depolarize, so like when you're all the way up here and you're depolarized, well, what does your cell look like? Okay, so remember here you are negative 70 millivolts at rest. Well, when you're depolarized all the way here, remember you're positive on the inside because you hit positive 40, and you're negative on the outside. And then right here, you are repolarizing, and remember when you are repolarizing, which is this region over here, when you're repolarizing, and this part here was depolarizing, remember, when you're repolarizing, you are negative on the inside and positive on the outside. And that is because, okay, let's just go back to this depolarizing. So just remember, why are you so positive on the inside here? Because you have both potassium and sodium on the inside. That's why you're so positive, because both of them. And why are you negative again and positive over there? Because remember, all the potassium are leaving. So now you have lots of potassium on the outside and sodium is kind of stuck inside. And then you want to go back to rest. And what restores resting membrane potential? So you reverse the potassium and the sodium, so you get back to what you started with. You use your sodium-potassium pump. And that is how the action potential works. One quick thing about the action potential and how it works is, like, you know, when you look at a neuron, right, you got to look at a neuron in sections, right? Like, imagine this is your axon, okay? And when you look at your axon, right, remember how I said, like, there's all these channels on your axon? So, like, there's the sodium channel, and there's the potassium channel, and then there's the sodium-potassium pump. Okay, so when you look at this, right, and let's say, like, using our salt example, right, let's say you have enough salt, and, you know, because of the salt, you have sodium rushing in here. Okay, so, right, when you look at this diagram here, you can see that because sodium and potassium on the inside, this must be positive 40 millivolts. This part of the neuron is depolarizing, right? And you can even look at this diagram here, like, this part is at rest, okay? Like, the whole neuron right here is at rest, right? But what I'm trying to say is, like, the action potential, right? Let's say if it's depolarizing right here, right? And because you put salt in it, and so the sodium channel's open, the part right in front of it is still at rest, okay? Like, it's not like if this part of the neuron is depolarizing, the whole neuron is depolarizing. Only this section of the neuron depolarizes, right? So I'm just showing you this section of the neuron was depolarized, but right in front of it, right, it's still at rest, meaning sodium here is on the outside and potassium here is on the inside, like that, okay? But how do I make that region, right? How do I make this region that's at rest, so this region is at negative 70 millivolts, how do I depolarize that particular region? Well, when you allow sodium in, okay, so remember with sodium, remember we have a high concentration of sodium here, right? Well, do you see, because I have such a high concentration of sodium here, because I'm depolarizing and my sodium channel's open in response to salt, so now the sodium rushes in, right? Because I have all the sodium on this region of the neuron, this sodium will diffuse to this region of the neuron. And if sodium moves to this region of the neuron, what's going to happen to my negative 70? Well, it's going to become more positive. And if enough sodium diffuses that you get to negative 50 millivolts, that means all the sodium channels in this region are going to open and the sodium is going to rush in this region too. And this region will depolarize. Now the region in front of it is still at rest, right? But with the sodium rushing into this region, again, the sodium ions will diffuse and will cause the sodium channels in the region beside it to open as well. And this is what we call the propagation or the movement of the action potential. Okay, it's just basically saying if you depolarize one region of the neuron, the sodium will move and diffuse from that one region where it's depolarized to the region that's at rest. And because sodium is diffusing, right, and all these positive charges are causing that negative 70, that region that was at negative 70 at rest, to become positive, like until it hits threshold, well, then all the sodium channels in that region open and the movement of the action potential continues. Okay, so that's what that means. Propagation means the movement of the action potential, and action potential just means like nerve impulse. Okay, so hopefully that makes sense. myelinated neurons are faster impulse than non-myelinated neurons, and that's because if you have a myelinated neuron, so I'll show you. Remember I talked on my last lesson about the myelin sheath. Well, when you have a myelin sheath, it surrounds, this is your axon. The thing is when, that means the sodium channels are just located here in the nodes of Ranvier. That's where the sodium channels are. So here's another, okay, node right here. So a node is the gap, okay, the gap between myelin. So this, you guys, here is the myelin sheath. So that's the myelin sheath. And the gap between the myelin is called the node of Ranvier. So this is the gap between the myelin sheath. And like if sodium is here, okay, and sodium diffuses in here, and now this is lots of sodium, and this region becomes polarized, and now you're positive 40 millivolts. Well, the sodium will diffuse to this node, and the sodium will cause that part of the neuron, that node here, to depolarize. And do you notice that there's no channels where the myelin is? And that's because the myelin doesn't allow charged ions through, right? Doesn't allow charged ions through. So the charged ions can only pass where the nodes are, right? And so sodium can only enter, right, the axon where the node is. Sodium cannot pass through the myelin. And because sodium can enter where the nodes are, and only where the nodes are, the impulse is actually faster, okay? So again, right, here is this part of the axon with a naked, like it's a naked axon, it's not covered in myelin. Sodium rushes in to this part of the axon, so you get lots of sodium here, and sodium will actually diffuse very quickly to this part. So this part was at -70, but because the sodium diffused here, it became all of a sudden -50, and so the sodium channels open here, and the sodium rushes into this region too, and depolarization occurs. Okay, so myelinated neurons conduct impulses faster than non-myelinated neurons. Also, how do you perceive, okay, so I just want you guys to know, like, how do you perceive between like hot versus cold? Well, just to know, different neurons have different thresholds. So that just means if you have a threshold at -50 millivolts versus a threshold at -10 millivolts, where do you think it would be harder to feel something? Would it be easier to get to -50 and harder to get to -10, right? So this would be like, this is like light touch, right? It's easy to feel light touch, but you have to put more pressure to feel like, so you're gonna have more pressure to feel like pain, right? So the threshold for pain is actually going to be harder to get than the threshold of light touch. Like let's say if at -50, let's say like somebody lightly touches you and your threshold is -50, and imagine that if somebody lightly touched you, and every time they lightly touched you, that you felt pain, and your threshold for pain was the exact same as light touch, that the threshold for pain was -50, the same as light touch, -50, right? That wouldn't make any sense. So it has to be that light touch has a different threshold than pain, right? And that it's easier to get to light touch than it is to pain, right? Because any little kind of brush against your face would make you cause pain, right? So different neurons have different thresholds. Also, if you activate more receptors, you're gonna feel more. Okay, so like imagine if you have these receptors being activated because like somebody's like poking you versus like somebody not poking you as much, and then the receptors are not as activated, so these ones are gonna be firing, right? Also, like different neurons, like watch this, like look at the rest period here versus the rest period here. So you can see the neurons are firing with increased frequency here. The neurons are firing with decreased frequency here. So this one would be like you feel warm. And this one would be like you feel hot, like your neurons are firing fast, 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 fast. And remember, like the neuron never goes above positive 40 millivolts, okay? Like that's the maximum. So the only way you can distinguish between hot and cold is your neurons firing more versus less, right? Which allows you to distinguish between that. The time it takes to go back to rest is called your refractory period. Okay, so that's what it's called. That's the time it takes to go back to rest. I know this was long. I'm sorry. There was so much information I tried to jam pack into this lesson. I hope it made sense. Okay, we're done.